Good morning, leaders. Good morning, sir. This is Tara Marie Valdez-Zabaja, the first reporter of the special machining topic. For many years, industry manufactured its products from a relatively small group of metals. Engineers made extensive use of cast iron, brass, bronze, soft steels, cast steel, and carbon and high-speed steel. Broaching is one of the fastest methods of removing metal. It is particularly useful in the mass production of intricate internal and external shapes. What is a broach? A broach is a cutting tool made up of series of cutting edges. Is the beginning hole drilled? The beginning hole can be drilled or cored in a casting. The finished hole can be round, square, rectangular, or irregular in shape. How was the broaching operation first developed? Broaching operation first developed when taper drift punches were driven by hammer through a piece of metal to form a larger or different shaped tool. Can the broaching operation be used on all types of jobs? Broaching is used on a full range of work size jobs, from the very small parts of a delicate instrument to the large castings of the engine block of a heavy truck. What are the different types of broaching machines? There are three types: the vertical, horizontal, and continuous chain broaching machines. What determines the type of machine to be used? A job on which a long broach must be used will require a horizontal stroke because of the space requirements. How are broaching machines driven? They can be driven either hydraulically or by electric motors. In what direction does the cutting action of the broaching tool take place? The action of the broach can be pull up, pull down, press, or push depending on the kind of work, the size of job, and the degree of accuracy and smoothness of finish required. What factors determine the length of the broaching tool? The length of the broaching tool is determined by the amount of metal that must be removed. What limitations are recommended for the length of a broach? The length of a push-type broaching tool should not exceed 25 times the diameter of finishing teeth. What are the sizes of broaching tools? The sizes range from 0.050 to 20 inches in diameter. Are all teeth on the broach identical in shape? There are three types of teeth on the typical broach: roughing, semi-finishing, and finishing. What determines the distance between the teeth? The distance between the teeth, called the pitch. It is determined by the length of the cut, the material being cut, and the size of the tooth gullet. What determines the size of the tooth gullet? The size of the tooth gullet is related to the material to be cut and the type of chips produced. Why are the teeth of some broaches shear-angled? A broach with shear-angled teeth gives a better surface finish and will reduce tool chatter. What provision is made to break up the chips during the cutting operation? Notches, called chip breakers, are ground into the roughing and semi-finishing teeth to eliminate chip packing and allow for chip removal. Of what material are broaches made? Most broaches are made of high-speed steel. Others have inserted carbide cutting edges braced onto the body of the broaching tool. Are cutting fluids used in the broaching operation? A flat-bottom gullet allows space for more chips between teeth. Okay, let's proceed to honing. Because of the high speeds of rotating machine parts, designing engineers must consider the bearing surfaces and their problems. What is honing? Honing is a machining process similar to grinding. It is mainly used to finish bore surfaces. How does honing differ from grinding? Grinding machines are run at high speeds and high wheel pressure. In what other way does honing differ from grinding? The abrasive stone used in the honing machine have a relatively large area of abrasive in contact with the job. Is honing a manual or power operation? In machine honing, the abrasive carrying mandrel is power-driven. How accurately does the honing process finish a hole? Dimensional accuracy to 0.0001 inches is common. Tolerances to 0.00025 inches are easily obtainable. What kinds of materials can be worked by this process? Almost every material can be efficiently honed. Steels of all varieties, cast iron, aluminum, magnesium, brass, bronze, glass, ceramics, hard rubber, graphite, and silver are a few examples. Will the honing tool correct an out-of-round bore? By means of two unevenly spaced metal guide shoes, which are part of the honing tool. Can other bore imperfections be corrected by this process? Holes that are tapered, barreled, or bell-mouthed can be made straight and parallel. What other hole defects can be corrected by the honing technique? Honing corrects the problems left by over-operations that results in holes that are misaligned, undersized, or have marks left by reamers and boring tools. Is it possible to hone workpieces of a wide range of shapes and sizes? Honing machines are made in different sizes and can handle many different types of work. How are the workpiece and the abrasive kept cool and clean? Our servo tank, which is a part of the machine, hold many gallons of industrial oil, which is pumped from the tank and can be directed on job and bundle. How does the disintegration process work? Metal disintegration is an electrical process that will produce a desired hole in any material that will act as a conductor to electrical current. What results from the removal of metal at the arc? A correctly sized hole will be made in the workpiece as a result of intense heat at the arc. What is the temperature at the end of the disintrode? A temperature of 5,000 degrees Celsius occur at the tip. Does the intense heat affect the material around the hole? No, because of the rapid action of the coolant. Can holes of various sizes result from this process? Disintrodes from 0.030 inches to over 0.750 inches can be used. Can holes of different shape be made in hardened materials? The holes will conform to the shape of the disintrodes, which are available in many shapes. What type of job is the metal disintegrator used for? It can be used to drill bolt holes, coolant holes, lubricant holes, in fact, holes of any shape in any kind of metal. The hydroforming process. For many years, mechanical and hydraulic presses have been used to stamp out metal blanks to special and intricate shapes. How does the hydroforming process differ from the mechanical type of press forming technique? Hydroforming requires the use of one accurately shaped die. Why is only one shaped die necessary? The matching die is flexible pad force against the blank. What is the main advantage of the hydroform process? The fluid forming process applies the forces around the blank with uniform pressure and wraps the blank around the shaping die. What other advantages are there in this method? Only a single die is required instead of a closely matching pair. Less storage room is required, fewer dies are necessary, and the smooth wraparound method of forming puts less strain on the metal and leaves a smooth surface which requires no further finishing. Does this method require larger size blanks? The hydroform method does not need a mechanical device to hold the blank.
Hello everyone, my name is Ria May Saicon and I will be the second reporter for this topic. Now, let's talk about electrochemical machining process. Electrochemical machining process, or also known as ECM, it is a method of removing materials or machining materials that are difficult to machine. So, to explain that, electrochemical machining process, or ECM, is all about removing materials, and especially made to remove materials that are difficult to machine or those extremely hard ones. The most common tools that are used in this method are brass, copper, and bronze. So many will ask, how does electrochemical machining works? So it works when an electrical current passes through an electrolyte in the space or gap between the workpiece and a specially shaped tool. To add with that, electrochemical machining, or ECM, is a way of machining a part without having any contact between the tool and the workpiece. The metal is dissolved and carried away by the electrolytic solution. The workpiece is charged positively and the tool negatively, and between the two pieces there's a tiny gap who don't actually touch, but there's an electrolyte fluid between the two that slowly removes atoms. And as the tool slowly moved out towards the workpiece, more and more atoms are removed until the workpiece conforms to the same shape as the tool. Now, let's talk about the advantages and disadvantages of ECM. The advantages of ECM is that it can be used on the hardest metals. Also, it can be used on the thin and delicate work without the job becoming out of shape. And lastly, the completed job shows almost no distortion because of the very little heat generated. While the disadvantages of ECM is that the equipment is very expensive and the electrolyte may attack or corrode some metals. The next one is the electrolytic grinding. The electrolytic grinding, or ELG, removes metal by electrochemical decomposition, and it dissolves materials from the positive electrode, which is the anode, and deposit it on the negative electrode, which is the cathode. How is the process used in electrolytic grinding? Similar to electrochemical machining, this process is a combination of grinding process and electrochemical machining. It is also known as the anodic machining. The workpiece is made to act as an anode, while the grinding wheel as the cathode. The workpiece is electrically connected to the plus terminal of a DC power source. The electrolyte then is injected into the space or gap between the wheel and the job. The circuit is completed and the electrical current flows from the workpiece to the wheel through the electrolyte, electrochemically dissolving the surface of the workpiece. There are 7 equipments required in electrolytic grinding. The first one is the DC power supply, the electrolyte tank, the reservoir, the electrolyte, the circulating system, the nozzle, and the grinding wheel. Proceeding to the advantages and disadvantages of electrolytic grinding. The advantages of ELG is that it can grind very thin materials for about 1 millimeter. The second one, machined areas are burr-free. The third one is that there is no hardening and cracking of the workpiece. The fourth one, the grinding wheel requires less frequent dressing. The fifth one is that no heat is generated. The last one, the process is faster compared to traditional grinding process. While the disadvantages of ELG is that it has high consumption of electricity, electrolyte may have a corrosive effect, and the process is not economical for soft materials. The next one is the electrical discharge machining. So what is electrical discharge machining? The electrical discharge machining, or also known as EDM, is a process that removes metal by utilizing an accurately controlled electrical spark or discharge. These discharges are repeated many thousands of times per second in the selected area of the workpiece. So how is it possible to machine a job to accurate size and shape by this method? Well, you need to have full control of the voltage, the amperage, the capacitance, and the frequency. By this, the shape of an electrode tool can be imparted to the job. This can be done either as a through the hole or as a cavity impression. Both roughing and finishing cuts can be made by this process. What are the components and functions of a typical EDM system? Well, the following descriptions are extracted from the Fundamentals of EDM published by the EDOC Corporation, a leading manufacturer of EDM equipment. So the 6 components and functions of a typical EDM system are: 1. The power supply, 2nd. The machine tool, 3rd. The electrode, 4th. The amperes, the 5 is the overcut or spark length or spark gap, and the last one is the dielectric. The last topic in my report is the laser in industry. The laser is a relatively new tool in the metalworking industries. Although its potential applications in many fields are still being developed, many applications have become commonplace and are no longer merely of interest in the laboratory. What is a laser? A laser is a device that can concentrate a light beam in a very narrow path. How did laser get its name? Well, it is derived from the first letters of the words. That means light amplification by stimulated emission of radiation. Who developed the first laser and when? Dr. Theodore H. Maiman demonstrated the first ruby laser in the Hoggs Research Laboratories in Malibu, California in July 1960. The scientists in the Bell Laboratories developed the first gas laser using a mixture of helium and non-energized by a radio frequency generator in 1961. How is the laser beam generated? It was generated when electrons in the atoms in optical materials like glass, crystal or gas absorb the energy from an electrical current or a light. Lastly, I will be discussing the three types of laser. First, the ruby laser, the gas laser, and the injection laser. The first one is the ruby laser. The ruby laser was the first laser used to optically pump tunable dye lasers and is particularly well suited to excite laser dyes emitting in the near infrared. The second one is the gas laser, in which an electric current is discharged through a gas to produce a coherent light. The third one is the injection laser, also known as a diode laser, is a semiconductor device that produces coherent radiation in which the waves are all at the same frequency and phase in the visible or infrared spectrum when current passes through it.
Surface finish. An engineering component may be cast, forged, drawn, welded, or stamped, etc. All the surfaces may not have functional requirements and need not be equally finished. Some surfaces, owing to their functional requirements, need additional machining that needs to be recorded on the drawing. Surface roughness. The geometrical characteristic of a surface include macro deviations, surface waviness, and micro irregularities. The surface roughness is evaluated by the height, RT, and main roughness index RA of the micro irregularities. Surface roughness number represent the average departure of the surface from perfection over prescribed sampling length, usually selected as 0.8 mm. Surface roughness number RA is expressed in microns. The measurements are usually made along a line running at right angle to the general direction of tool marks on the surface. Actual profile. It is the profile of the actual surface obtained by finishing operation. Reference profile. It is the profile to which the regularities of the surface is referred to. It passed through the highest point of the actual profile. Datum profile. It is the profile parallel to the reference profile. It passed through the lowest point of the actual profile. Mean profile. It is the profile within the sampling length chosen L such that the sum of the material field areas enclosed above it by the actual profile is equal to the sum of the material avoid area enclosed below it by the profile. Peak to the valley height. It is the distance from the datum profile to the reference profile. And mean roughness index. It is the arithmetic mean of the absolute value of the highest height between the actual and mean profile. And this is the data of manufacturing and manufacturing process.
Measurement of roughness. The roughness may be measured using any of the following: straight edge, surface gauge, optical flat, tool markers, microscope, profilometer, profilograph, tailor surf. Indication of surface texture. The basic symbol consists of two legs of unequal length inclined at approximately 60 degrees to the line representing the considered surface. The symbol must be represented by thin line. If the removal of material by machining is required, a bar is added to the basic symbol. If the removal of materials is not permitted, a circle is added to the basic symbol. When special surface characteristics have to be indicated, a line is added to the longer arm of any of the above symbols. Basic symbol only be used alone when its meaning is explained by a note. Indication of surface roughness. The value or values defining the principal criterion of roughness are added to the symbol. Our roughness is value. A is equals to the surface roughness value. Roughness obtained by any production process. Roughness A obtained by removal of material by machining. Roughness A shall be obtained without removal of any material. And the first, if it is necessary to impose maximum and minimum limits of the principal criterion of surface roughness, both values shall be shown, like in the shown in the picture, like A1, A2, maximum limit A1, and the minimum limit is A2. If it is required that the required surface texture will be produced one particular production method, this method shall be indicated in plain language on an extension of the longer arm of the symbol, like in the shown video. A in a mild indication of machining allowance where it is necessary to specify the value of the machining allowance. This shall be indicated on the left of the symbol. These values shall express in millimeters, like in the picture. A dash in the above is millimeter. 5. Generally, to indicate the surface roughness, the symbol is used instead of value. The relation is given in the following table. That table shows the surface roughness and its symbols. Machining symbols. Optional 3.2 or N8. Obligatory 3.2 or N8 in that shown data. This symbol may also be used in a drawing relating to a production process to indicate a surface is to be left in the state resulting from a preceding manufacturing process, whether this state was achieved by removal of material or otherwise. Position of the specification of the surface texture in the symbol. The specification of surface texture shall be placed relative to the symbol as shown in the picture. Roughness value RA in micrometers or roughness grade number N1 to N12 and B is equals to production method, treatment, or coating. C is equals to sampling length. D is direction of lay. E, machining allowance. F, other roughness value in brackets. Symbol. That symbol, in the first symbol, parallel to the plane of projection of the view in which the symbol is used. Tapos, next symbol is like T na upside down, perpendicular to the plane of projection of the view in which the symbol is used. X, cross into slant direction relative to the plane of projection of the view in which the symbol is used. M, multidirectional. C, approximately circular relative to the center of the surface to which the symbol is applied. R, approximately radial relative to the center of the surface to which the symbol is applied. Symbol and its meaning. First is production method milk, and the second is sample length 2.5 millimeter. And the next symbol is direction of lay, perpendicular to the plane of projection of view. And the fourth symbol is machining allowance to 2 millimeter. And then the last is indication in brackets or criterion of roughness other than that used for RA. For example, R is equals to 0.4 millimeter. If it is necessary to define surface texture both before and after treatment, this shall be explained in a suitable note or in accordance with figure. The direction of lay is the direction of the predominant surface pattern ordinarily determined by the production method employed. If it is necessary to control the direction of lay, it is specified by symbol added to the surface texture symbol. Ways to represent surface, as shown below. That is the example ways of to represent what symbol in the surface.
So good morning everyone. My reporting is all about testing of metals. So testing of metals. Metal testing is accomplished for the purpose of estimating the behavior of metal under loading, tensile, compressive, shear, torsion and impact, cyclic loading, and etc. of metals, and for providing necessary data for the product designers, equipment designers, tools and die designers, and system designers. So therefore, the test procedure for developing standards specification of materials has to be evolved. Uh, the necessities both destructive and non-destructive testing of materials. Destructive tests of metal include various mechanical tests such as tensile, compressive, hardness, impact, fatigue, and creep testing. A standard test specimen for tensile test is shown in figure 7.2. So, tensile test. A tensile test is carried out on a standard tensile test specimen in universal testing machine. So, here in the picture, as you can see in figure 7.3, this shows the systematic setup of universal testing machine reflecting the test specimen grip between two cross heads, while in 7.4, it is the figure shows the stress strain curve for ductile materials. So we have compression test. Compression test is a reverse tensile test. This test can also be performed on a universal testing machine. In case of compression test, the specimen is placed bottom crossheads. After that, compressive load is applied to the specimen, to that test specimen. So this test is generally performed for testing brittle materials such as cast iron and ceramics. So Hooke's law. Hooke's law states that when a material is loaded within elastic limit up to proportional limit, stress is proportional to the strain. So it states that for relatively small deformation of an object, the displacement of or size of the deformation is directly proportional to the deforming force or load. Next is strain. Strain is the ratio of change in dimension to the original dimension. So strain is the deformation of a material from stress. It is simply a ratio of the change in length to the original length. Next is tensile strain. The ratio of increase in length to the original length is known as tensile strain. So in other words, tensile strain is produced when a body increased in length has applied forces to try to stretch it. Next is compressive strain. The ratio of decrease in length to the original length is known as compressive strain. So in other words, compressive strain is produced when a body decreases in length when equal and opposite forces to compress or squeeze it. Next is modulus of elasticity. The ratio Next is modulus of elasticity. The ratio of tensile stress to tensile strain or compressive stress to compressive strain is called modulus of elasticity. It is denoted by E. It is also as Young modulus of elasticity. So E is equal to tensile stress or tensile strain. Next is modulus of rigidity. The ratio of shear stress to shear strain is called modulus of rigidity. It is denoted by G. So G is equal to shear stress or shear strain. Next is bulk modulus. The ratio of direct stress to the volumetric strain or ratio of change in volume to the original volume is known as volumetric strain is called bulk modulus, which is denoted by K. So K is equal to direct stress or volumetric strain. Next is linear and lateral strain. When a body is subjected to tensile force, its length increases and the diameter decreases. So when a test specimen of metal is stressed, one deformation is in the direction of force, which is called linear strain. Another deformation is perpendicular to the force called lateral strain. Next is Poisson's ratio. The ratio of lateral strain to linear strain in metal is called Poisson's ratio. Its value is constant for a particular material but varies for different materials. Next is proof resilience. The maximum amount of energy which can be stored in an elastic limit is known as proof resilience. Modulus resilience. The proof of resilience per unit volume of a material is modulus of resilience or elastic toughness. So we have here testing of hardness. Testing of hardness, it is a very important property of the metals and has a wide variety of meanings. It embraces many different properties such as resistance to wear, scratching, deformation, and machinability, and etc. It is also means the ability of metal to cut another metal. The hardness of a metal may be determined by the following tests. A. Brenner hardness test. We have second B. Rockwell hardness test. C. Vickers hardness, or also called the diamond pyramid test. And the last one is D. Shore scleroscope. So right here we have testing of impact strength. The impact test measures the energy necessary to fracture a standard notch bar by an impulsive load, and as such is indication of the notch toughness of the material under shocking loading. ISO test and the Sharpie tests are commonly performed for determining impact strength of materials. So when the metal is subjected to suddenly applied to load or stress, it may fail. In order to assess the capacity of metal to stand sudden impacts, the impact test is employed. So we have here the figure 7.10 in the picture. So in this figure shows the impact testing setup arrangement for Sharpie test. The specimen is held in a rigid vise or support and is struck below by traveling pendulum that fractures or severely deforms the notched specimen. Next we have testing fatigue. So material subjected to static and cyclic loading, yield strength is the main criterion for product design. So for dynamic loading condition, the fatigue strength or endurance limit of a material is used in main criteria used for designing of products subjected to repeated alternating stress over an extended period of time. So testing of creep. Creep is time-dependent phenomena of metal failure at high constant stress and at high temperature, such as subjecting of at steam turbine blade. So metal part when is subjected to a constant stress at high temperature for a longer period of time, it will undergo a slow and permanent deformation or in form of a crack which may further propagate further towards creep failure. So we have here choice of material for the engineering application. The choice of materials for the engineering purposes depends upon the following factors. So number one, we have availability of materials. So the type of materials availability of check depends on the time available for executing orders. So it means that all material must be available before the order can be released and executed. Number two, properties needed for meeting the functional requirements. So getting the requirements right is the key to the success of any projects. Failure to accurately define and document them may lead to results miscommunication. So number three, we have suitability of the material for the working condition in service. So by that, choosing the right materials when manufacturing is a new product is vital for its success. So the last one is the cost of materials. So it means that material control lies in fact that any saving made in the cost of materials will go a long way in reducing the cost of production and improving the profitability of a concerned product.